So thanks so much for this kind invitation and the opportunity to share some of my recent work. As Sami said, I'll be talking about scientific exploration, and I'll be talking about explainable artificial intelligence, and I'll try to propose some ideas of how recent methods in explainable AI can contribute to certain specific kinds of exploratory practices that some philosophers of science have recently discussed in the literature. So this will be very much a kind of a coming from a philosophy of science perspective, but I hope to kind of make a bridge and show, on the one hand, how philosophical work is relevant maybe for scientific exploration in practice, but then also, of course, what interesting philosophical lessons we can extract from recent work in scientific exploration. So just kind of to orient ourselves and to see where exactly I want to come into this discussion. Most of the audience is probably familiar with the fact that certain methods and models developed using machine learning is, of course, becoming very prevalent in scientific research. So, for example, in astrophysics to discover exoplanets, in neuroscience to kind of interpret fMRI images, or in medical diagnosis, right, to diagnose diseases from certain patient symptom profiles. What has, of course, emerged as kind of a challenge in the last 10 years or so is the opacity of these machine learning models. So it's often quite difficult to understand why they do what they do or how they work, right? Of course, we need to cash out the senses of why and how. I've done that in previous work, and I will briefly touch upon that here. But basically, we can say that, well, a lot of these machine learning models, some of which are deep neural networks, are, of course, very large and complex. And it's difficult to say what any individual parameter or variable is doing in the model. And of course, these models are not hand-coded, so programmers don't determine what the values are for any particular parameter, let's say, right? But there's some kind of automatic process, right? Interactions between learning environment data and learning algorithm that determines the values of these parameters. So there's a very hands-off sense in which they're developed, and therefore we don't really know anymore what is going on in these models. And that's kind of a very intuitive sense in which these models are often opaque. Then what, of course, kind of computer scientists are always up to whenever they see a problem, then they immediately start working on possible solutions. And one proposed solution is this research program of explainable AI, or XAI, explainable artificial intelligence. The main idea here is to develop methods with which to render these kind of opaque models transparent. So, for example, and I think the second talk today might go into these methods in a bit more detail, right? You've got kind of saliency mapping techniques that identify high responsibility input elements for certain outputs. You've got surrogate modeling techniques, you've got counterfactual explanations, linear approximations, many different models that are used to somehow shed light on what these opaque systems are actually doing. So the question I want to ask is, what role can these kind of methods play in scientific research? So I won't be discussing the role of machine learning in a general sense. I'll be homing in on the question of the possible role of these kind of XAI techniques, these kind of linear approximators, saliency maps, and so on and so forth, for scientific research. In particular, what I want to look at is not scientific research as a whole, but one particular aspect of scientific research, which is very interesting, in part because it's been neglected in the philosophy of science, which is scientific exploration. So very often when scientists kind of come up with new experiments or come up with new possible explanations for something they observe, or even new phenomena that they want to explain, right, it's often left unquestioned or uninvestigated how they actually come up with these explanations, how they come up with these experiments to run, or how they choose that this phenomenon should be one that should be investigated as opposed to some other phenomenon. And to a certain extent, this kind of situation where we've neglected this kind of choice of explanations or experiments and so on, this is in the last 10 years or so in philosophy of science has received a lot of attention. And so what I want to do is I want to feed into this debate as to how scientists conduct certain exploratory activities. So specifying new target phenomena, identifying experimental starting points, or articulating possible explanations with the help of tools from explainable AI. And the claim that I want to make is, in fact, that these tools can play an important role in these kind of exploratory activities, which I will explain one by one in detail. So let's kind of start from the beginning of Explainable AI and what it was actually meant to do, what it's designed to do, and why we even care about Explainable AI in the first place. And that's, of course, to address this challenge posed by opacity. Now, opacity is, of course, it's a metaphorical notion that deserves some close analysis, and that's in part what philosophers do, is they analyze terms, try to define terms and understand what they mean. And so looking in the literature, one of the protagonists in this debate who actually arguably coined the term of opacity in the context of computer simulations and computer models in scientific research is Paul Humphreys. And Paul Humphreys, back in 2009, defined opacity as, or defined a computer simulation or computer model to be opaque when so he says a process is epistemically opaque relative to some cognitive agent X at time t, just in case X does not know at t all of the epistemically relevant elements of the process. It's, of course, a very philosophical definition. Two things that should immediately pop out of this definition is, on the one hand, that opacity is agent relative. So systems are not opaque in their own right, but are opaque only to particular users of the system or of the model of the process. Then also opacity is an epistemic phenomenon. It concerns the lack of a certain kind of knowledge, right? And in particular, what Humphreys here calls knowledge of epistemically relevant elements. Now, of course, the question immediately is, what are the epistemically relevant elements of a system? And here I've argued in previous work that there are many different kinds of epistemically relevant elements. So, of course, most intuitively, we could think of kind of deep neural networks, variables or parameters, right? So such as unit activations or connection weights, right? These are things that we could, in principle, look at to help us explain the system's behavior, better understand what the system's behavior. But of course, as we know from the size and complexity, basically from the number of these parameters and their nonlinear interactions, it might not always be very useful to look at those elements as opposed to other elements. And that's why many researchers or many users of machine learning systems, they look at certain higher mathematical or computational structures. So such as learned representations, abstractions that are somehow being tracked by the system, or certain manifolds that we look at how variables change with one another or relative to one another given certain inputs or over time. So the challenge here is to kind of abstract or extract these kind of mathematical or computational features from the system and see if we can explain the system's behavior by appealing to them. Of course, we could also explain the system's behavior differently. We could look at the hardware level, look at electromagnetic properties of certain hardware components, right? That's a very legitimate way of explaining a system's behavior. It might not always be the best way of explaining it, but it is one way of explaining systems behavior. We can also, of course, appeal to external causes. So, for example, the input elements. If it's an image classifier, then these are often pixel values, right? And we can say, okay, because certain pixels had certain values, therefore the outputs were as they were, right? So here we're getting at an explanation of those outputs by appealing to certain input values. We can also, and this is of course a very philosophically loaded term, is try to identify the reasons for which a certain machine learning system acted, right? I don't want to be too inflationary here with the term reasons, but the idea, my idea when we're looking at reasons, what we're looking for here is features of the environment that the system has learned to track or recognize or identify. So for example, if the system has learned to identify chairs in the environment and then give certain outputs on that basis, right, then we are speaking about the reasons for giving certain output. Or why is the system discriminating? Well, because it is classifying, for example, the quality of a potential employee based on their gender or based on their race, right? Those are the reasons why it gave that decision. And in this case, it's a bad reason, okay? So all of these kind of things, hardware components, variables, parameters, also these more abstract reasons, which are basically features of the environment that are being tracked. These are all what Humphreys would have called epistemically relevant elements. They're features or things, properties of the system or its immediate environment that help us explain how the system works, or why it does what it does, or what it is actually doing. And if we lack knowledge of these elements, then the system is opaque. When we possess knowledge of these kind of things, then we render those systems transparent. And I said, remember that opacity is agent relative, right? So there are many different types of agents, and they all need knowledge of different kinds of epistemically relevant elements in order to play their roles in what I would want to call the machine learning ecosystem. So here's, I'm taking this ecosystem from recent work by Richard Tomset, right? Where he identifies different actors or stakeholders that regularly interact with a machine learning system. So the ML ecosystem contains several different agents or stakeholders, right? And they all possess different knowledge and have different abilities, and they perform different roles. So, for example, creators are usually programmers or hardware technicians, systems engineers that are charged with building, improving, maintaining, or fixing a system, right? But in order to do that, they need knowledge, right, of variables and parameters, right? They need to be able to know, okay, what are the actual parameters that are, for example, that constitute the weights of the network, right? They might also want to know, in order to, for example, diagnose a bug, right? They might also want to know something about these higher mathematical computational structures. So they might say, oh, the system is representing properties such as gender or race, which maybe it should not be representing. And so we need to retrain the system in a way that avoids the system from learning these kind of representations. Another stakeholder or agent in the ecosystem is a decision subject. That's somebody who's affected by the decisions that are reached on the basis of the system's outputs. And decision subjects have certain legal or moral rights or even obligations, right? So they have right to information, right to explanation, according to the EU GDPR, right? They also have a certain obligation or a right to be autonomous agents whose lives are not predetermined by the outputs of AI systems. And in order to exercise those rights, they need to know the reasons for certain data-driven decisions that affect their livelihoods. So they have a right to know why their loan application was rejected, or they have a right to know why a doctor whose diagnosis is informed by an AI system, why they are providing that diagnosis as opposed to another diagnosis. So they want to know these reasons. Why is my credit application rejected? Is it because I earned too little, or is it because I have brown skin? Right? So they have a right to know these kind of reasons. And in order to exercise their roles in the ecosystem, to be responsible users of these things, right, they must be empowered to be given those reasons. Examiners are kind of like external regulatory bodies who are charged with regulating systems and overseeing their use. And so, for example, they are the people who are charged with identifying the fact that a system is discriminating, for example, by gender or race or some other illegitimate category. So, and here again, they also need to know the reasons why a system is acting the way they do, right? Or maybe also in order to identify those reasons, they can, consult an expert who will give them some mathematical analysis of what the system is doing, what kind of representations it has learned, what kind of abstractions it is operating, it is computing over, and so on and so forth. So here we have different users, stakeholders, or agents in the ML ecosystem, and they all kind of require different kinds of knowledge in order to perform their roles in the ecosystem. So how does this all relate to science in general and scientific exploration in particular? Well, scientific investigators are, for the most part, a special kind of examiner. What they want to do, so remember, examiners are like people who like regulate the use and try to interpret what is going on in these ML models, right? And scientific investigators are often similar to these examiners. They want to characterize certain statistical regularities that are identified in some data set. So let's say you have a data set, some astronomy data set, and they want to characterize certain statistical regularities in that data set in order to know, well, is this indicative of the presence of an exoplanet in a certain faraway solar system? And so what they want to do is they want to interpret the system's outputs. They want to have, well, why is the system giving me a certain output, such as a high probability for an exoplanet? Is it because it is actually tracking the presence of exoplanets? Or is it because it's detecting something else that might be confused for an exoplanet, but actually isn't, right? So they really want to know the reasons why a system is doing what it's doing. They also, for example, they aim to understand how a machine learning system solves a certain problem. So in particular, in AI and AI engineering, for example, we want to know why AlphaZero works so well, why it plays Go at the level that it does. How exactly is it representing the board when it makes a godlike move that we cannot explain the quality of, or we do not appreciate the quality of, but it has somehow learned to represent the game in such a way that it knows that this is the right move to make. And we have to try to understand how is the system representing the board and why does that lead to the right or a winning position in the game. So the point is that as long as scientists do not possess knowledge of these kind of reasons, right, or abstractions, right, then opacity can have negative consequences for scientific research. So, for example, Yarkoni and Westphal have argued that, well, science should be a predictive endeavor, not an explanatory endeavor. We can predict now, but we often don't know why those predictions are right, and that gives barrier on explanations. Andres Paez has argued that, well, the most we can hope for is something like a non-factive understanding, not a real explanation. On the other hand, people like Emily Sullivan have argued that really opacity itself has no negative consequences, although opacity may come with certain other problems. So clearly there's a lively philosophical debate here as to the negative consequences for opacity on scientific research. What has received relatively little attention is the possible positive consequences that putative solutions to the opacity problem may have for scientific research. And here's where, of course, explainable AI enters the game. So, as I said previously, explainable AI is used to render opaque machine learning systems transparent. And just to kind of look at a preliminary dichotomy, right, we have, of course, the dichotomy between interpretable systems on the one hand and post-hoc explanations on the other. Interpretable systems are like machine learning systems such as decision trees that are arguably more transparent than, for example, deep neural networks, right? Cynthia Rudin has been pushing the use of these kind of systems, although there's some debate about how transparent even decision trees, if they're sufficiently complex and powerful, how transparent they actually are. What I want to focus on here, so the examples I'm going to use are mostly post-hoc explanation methods. These are mathematical, statistical, computational techniques that are used to explain the behavior of some opaque ML model. And so different XAI methods deliver knowledge of different kinds of epistemically relevant elements. This is something I've argued in a recent paper in Philosophy and Technology. Feel free to contact me afterwards or look it up online. The idea is that some of these post-hoc methods are used to identify reasons. Others are used to characterize mathematical computational structures. Others are used to acquire knowledge of different kinds of EREs that are useful for different stakeholders or different agents in the ecosystem. But let's look at scientific research in general and scientific exploration in particular. So, as I said, right, explainable AI is designed to kind of avoid these negative consequences of opacity, but I want to go a little bit beyond here and say, okay, explainable AI is not just the solution to a particular problem, right? But it's actually makes a positive contribution to scientific exploration. And interestingly, the positive contribution of to scientific exploration that these tools give go over and above the contribution that the ML models to which these techniques are applied give in their own right. So having an ML model can itself already be used for exploratory purposes, but then applying certain XAI techniques to that model yields additional exploratory purchase. That's what I want to argue here. So what is scientific exploration? Right. So as I said, it's only recently in the last 10 or 15 years that scientific exploration has really come onto the radar for philosophers of science, and they've identified several different kinds of exploratory activities or several different goals of scientific exploration. I want to look at three of them. One of them is defining target phenomena. Right, when we are researching, for example, pandemics, we want to know in the first hand, well, what exactly is a pandemic? Which kind of dynamics, right? So infection dynamics do we want to explain, and which infection dynamics do we ideally want to counteract, right? We want to know what a pandemic is before we can explain how pandemics come to be and maybe how pandemics can be stopped. That's one exploratory activity, is specifying these kind of target phenomena. Another exploratory activity is identifying an experimental starting point for further inquiry. What kind of experiments should I conduct or could I conduct in order to learn more about, for example, how to prevent or combat pandemics, right? As I said, we often rely on scientists' kind of genius or like artistic ability to identify the right experiments. or at least when we read scientific papers, right, they often report an experiment, but they don't actually say how that experiment like came to be, how they had the idea for that experiment, and they don't maybe report all the experiments that they tried and that didn't give any results, right? So the interesting question here is, okay, how do scientists identify experiments that they want to conduct? Finally, what I want to look at is this generation of potential explanations for certain types of phenomena. So why do pandemics occur in some populations but not in others, right? We want to, in order to answer this question, we first need to have kind of a possible explanation or a candidate explanation, right? And then we can test that explanation, maybe through experiments. But how do we come up with that possible explanation in the first place from a logical space of potentially infinite possible explanations, right? How do we come up with one that is worth testing? So here are 3 exploratory activities, and I want to look at how XAI techniques can inform and drive all of those exploratory activities. So the first kind of XAI model that I want to look at is the saliency map, or what I call an input heat map. And these tools, pardon me for a second, are most often used on classifiers that have learned to map certain input values to certain output values. So a deep neural network that, for example, has learned to classify and identify cancerous melanoma, right? So it receives an input bitmap image of a skin sample, and then it classifies that sample according to what kind of discoloration it is, and in particular, whether it's cancerous or not. Now, we have XAI techniques that I won't go into detail as to how they work or what kind of techniques they are. One of them is prediction difference analysis, but also layer-wise relevance propagation. What they do is they highlight certain high responsibility input features. So if you look at the pictures below, we have original images on the top row. We have the weight of evidence on the bottom row. That weight of evidence is color-coded, red and blue. And so red are areas of the image that contribute toward a certain classification. Blue areas are areas of the image that speak against a certain classification. But in the end, then the classification was as it was. And what these tools let us know is which elements of the input, so in this case, which pixels contributed in what way to the generation of that output. So what can these kind of heat maps be used for? Well, they help us understand which environmental feature or regularity is being tracked by the model. Where is the model paying attention? Where is the model looking, so to speak? So they help us understand why the model does what it does by specifying semantically individuated reasons for its behavior, right? We can look at the heat map and say, it's picking up on these brown discolorations, maybe as opposed to these red discolorations, or it's picking up on discolorations of a characteristic shape as opposed to other discolorations. Now, Emily Sullivan, my colleague in Eindhoven, she has argued that this goes a long way in determining the suitability of the model. So she has argued that these XAI tools can be used to kind of validate that it's a good model for this purpose. So what she argues is that, well, we can determine whether the neural network is tracking a known causal relationship between color spots and malignancy, as opposed to tracking a spurious correlation between, for example, freckles and malignancy, something that we know is irrelevant and should not factor into a decision. And so she says that, in fact, okay, the system can be used in this way, and we can validate the model using these heat maps. And that's all fine and good. However, but these models, arguably, and this is going beyond Emily's paper, these kind of XAI techniques also serve the purpose of determining with more precision what melanoma actually look like. So if we look at these heat maps and we see what are the features that they are focusing on in order to identify melanoma, we can maybe improve our understanding of what melanoma characteristically look like, right? So if they are systematically looking at certain types of shapes, let's say shapes of melanoma that have Mickey Mouse ears in that shape, as opposed to just purely round melanoma, we can maybe learn something about the characteristic shape of melanoma that are maybe malignant as opposed to non-malignant ones. So in other words, we can determine whether the model is tracking something that is previously unknown in the data. right? And interestingly here, this is something that the authors of this particular melanoma study, they do in fact pick up on. They say it's interesting to see that surrounding skins can be used as evidence to classify skin lesions in the CNNs. So it's not just the melanoma and the actual discoloration, it's the area around it. And so what we might learn from this is we might say, well, skin cancer, right, that is focused on the melanoma might also impact the skin surrounding the melanoma. And this might be something that we have not discovered yet. We do not know exactly how the skin around the melanoma is impacted. And the tool here tells us to look here closely because there's something here, some property of skin cancer that maybe we do not know, but that is useful for predictive purposes. So here, what I want to do just before moving on to the next example, right? This is to emphasize the fact that this exploratory goal is unlikely to be achieved through the use of ML models alone without the application of XAI techniques. So here again, Emily Sullivan's paper, she says that when she's talking about a certain ML model that is used for diagnostic purposes, she says that the model points to possible correlations that are worthy of future scientific and empirical research. And it is the patterns that the deep patient model indicates that gives researchers hypotheses to test and gain additional evidence for. So this is kind of exactly this kind of exploratory use of machine learning. But what Emily here overlooks is that it's not the model itself that is giving us these kind of indicators. It's applications of explainable AI applied to the model, right? The model itself does not point to or indicate anything. It merely transforms certain specific inputs into specific outputs. We need the XAI techniques to understand this transformation, to understand exactly what kinds of inputs are being transformed to certain kinds of outputs, right? And so this is exactly what the exploratory insight should be and is, at least insofar as we want to specify target phenomena more precisely, in this case, melanoma. So much for starting for phenomena and specifying phenomena. I want to now look at identifying starting points. So understanding a learned transformation is also an important starting point for future inquiry. So again, quoting from Emily's paper, which is definitely worth a read in case you haven't come across it yet. So more than this, it points to possible correlations that are worthy of future scientific and empirical research. This is exactly the same passage I quoted earlier, but highlighting the different aspects of it. It is the patterns that the deep patient model indicates that gives researchers hypotheses to test and gain additional evidence for the strength of these patterns in real-world cases. Exploring these hypotheses further would be useful. This is true, but it does not say anything about what kind of research should in fact be conducted. So yes, the idea here is right that machine learning can help us conduct further experiments, but how we again leave completely nebulous the question of how do researchers actually choose experiments to run? Which experiment should I do tomorrow, either this one or that one, assuming that experiments are, of course, resource intensive to conduct. So we want to know, well, which experiment now should I run of the many possible experiments I could run? Here I want to look at the particular area of causal inference. So determining whether an event C is causally relevant for an event E, given certain background conditions B. What we kind of know from previous philosophical research and research in causal inference in computer science, for example, is that causal inference is closely tied to counterfactual reasoning. So assuming that all background conditions B remain unchanged, we can infer that C is causally relevant for E. This should be an only if, it shouldn't be an if and only if a counterfactual change in C co-occurs with a change in E. So if we have some putative cause and an effect, and we modify the cause, keeping everything else constant, and we don't see a change in the effect, then we can conclude that the cause probably, or the putative cause, wasn't in fact the cause, right? So we cannot say, if both of them do in fact change, we cannot say that this was in fact a cause, because there might be things like common causes and things like that, right? But we can say, we can at least exclude the possibility if we find that we can turn this one off without affecting that. And so one important exploratory task that kind of guides experiments in this area is to uncover relevant counterfactuals on the basis of which to perform causal inference. So how should I exactly modify C in order to test whether it is in fact the cause of some possible effect E? Which events might be causally relevant for a particular outcome, and which experiments should be performed to test their causal relevance? Here, what I want to look at is the XAI method for counterfactual explanation. So this method is used to generate counterfactuals for certain desired outputs of a particular machine learning model. So for example, for a credit scoring model, right, a counterfactual explanation generator could tell you that you were denied a loan because your annual income was £30,000. If your income had been £45,000, you would have been offered a loan, right? So a non-factual input that would have generated a different output. There are some recent software tools, such as, for example, the Counterfactory, that implements this kind of general XAI method. It's model agnostic. You can use it to any ML system, a deep neural network for vision, as much as a credit scoring system. It doesn't really matter. But the idea is, okay, how can I use this for scientific purposes? One important caveat here is that in scientific context, the relevant machine learning models might, of course, be false, right? So if we have some diagnostic system, it might make predictions that are inaccurate. And for this reason, counterfactuals generated don't actually provide causal explanations. So if I change the input, I might get a different output in the model, but that might not actually be reflected in the real world, right? So we fall short of causal explanation, but what we do get is a possible hint for causal exploration, in the sense that we can now say, the counterfactory is telling us that if I modify this cause, I might get a different effect, at least in the model. Insofar as the model is correct, I should get a different effect. Now we can say, well, if the counterfactory is telling us that this modified input gives me that changed effect, let's go test that modified input. So that's basically a possible intervention at the level of the input that constitutes this kind of counterfactual reasoning. And we might use this, for example, in synthetic biology, right? We can use generated counterfactuals to identify and test genetic modifications that are likely to express certain phenotypic traits that are maybe desirable. Or in chemistry, we can use counterfactual explanations to identify and test new compounds with desirable pharmaceutical properties, right? So we have some model that kind of maps, for example, compounds to pharmaceutical properties, and then we run something like the counterfactory on it, and we say, well, if we modify the compound in this way or the other way, we should get a slightly different pharmaceutical property. And so now we have maybe an occasion to test exactly this change. So that's like an experimental starting point. Since I'm running short on time, I'll make this quick, right? One particularly interesting domain here, or it's interesting to keep in mind the fact that we might use this kind of causal inference, in particular in areas where causal inference is traditionally difficult. That's in the domain of high dimensional complex systems, right? And for the simple reason that we can develop ML models that replicates the behavior of these kind of complex systems. And we now have a counterfactory that it doesn't matter how complex the ML model is, it will give you counterfactuals. And so maybe we can use it for causal inference, in particular in this domain. So that's a particularly maybe promising or interesting application of explainable AI for scientific exploration. Here we go with the last kind of exploratory contribution. I'll make it quick. My background is in cognitive science and neuroscience, and I've always been very interested in this conception of, on this idea that explanations in cognitive science, so when we try to explain human or animal minds or behaviors, right, we want to come up with something like a computer algorithm that is implemented in the brain, and that computer algorithm, or sometimes we call it a cognitive model, is what is doing the explanatory work. We have a mathematical or cognitive or computational model that reproduces the behavior of the cognitive organism. And the question here is always, well, or the magic of cognitive science is that really, really clever researchers come up with really cool algorithms and models with which to replicate the behavior of some biological organism. But the question that is left unanswered, and that's the exploratory question, is how do they come up with these possible explanations? How do they come up with these candidate algorithms? And so the question I want to tackle here is, how can explainable AI help us here? And so one way in which it might help us here is through this XAI technique of surrogate modeling. Right? So surrogate modeling are relatively simple models that are trained, usually also machine learning models, that are trained to approximate a relatively complex ML model, such as a network's behavior or decision-making process. So one method is something like rule extraction, where from some deep neural network, we try to extract some symbolic rules to replicate or the same kind of decisions, or we extract some kind of tree that has a much simpler structure and arguably a more transparent structure than a deep neural network, but that reaches approximately the same decisions. Now, at first glance, and here we could take a deeper dive, but at first glance, these models very much resemble classic symbolic models that were used in cognitive science let's say up until the 90s, but even today, some people still use symbolic models as candidate cognitive models. We're talking about the symbols in the head or the decision nodes in the head that are responsible for the decisions we make. So just at first glance, if we train an ML model to replicate, to perform the same kind of behavior as a biological organism, and then we come up with a surrogate model to simplify, that approximates that ML model's behavior, that surrogate model might be a putative or candidate explanation that we can then test experimentally through psychological means or neuroscientific means. Another way, a more direct way that we can maybe come up with algorithmic hypotheses is through methods such as representational similarity analysis. So this is a method that is coming out of neuroscience, and it's just a mathematical technique to compare the activation of a neural network, either layer by layer or the whole network, and compare it directly to either the activation patterns that we observe in an fMRI signal, but also to compare it to certain features, let's say in a bitmap image. So, and the idea of this method, it allows us to characterize kind of the representation bearing structures in these networks. We can say, okay, certain patterns of activity correlate with certain features that we have in the environment. And then we call those patterns of activity representational structures for those features of the environment. And then we can compare those representational structures that, for example, we observe in a deep neural network with representational structures that we observe in fMRI imaging. So here, I don't want to go into detail for reasons of time, but Radek Kici and colleagues in Berlin, they used this kind of representational similarity comparing input images to artificial neural network to fMRI images to observe that, for example, the layers of the network, they seem to have like a hierarchical structure of representations. So representations change bit by bit while they go through the layer, and that this hierarchical structure is actually observable also in visual cortex in humans. So basically, they see that the representational processes in brains and in machines seems to be similar on the same kind of tasks. Again, this is very complex stuff we can discuss more in the Q&A, but the idea here is that we're using a tool to characterize what's going on in the network, and then we posit that the same kind of thing might be going on also in the human brain. So just kind of wrapping up this part, in a way, it shouldn't be wholly surprising if we do in fact find that machine learning models that are trained on naturalistic data sets will replicate the same kind of computational processes or learn the same kind of representations as human beings who are also engaged with the same kind of data, living in the same kind of world. So if we train these systems to perform similar tasks and train them on similar data, right, then arguably we might get similar algorithms. But of course, this is a very strong empiricist hypothesis. We don't have to defend it here. But what matters here is that XAI might help us test this hypothesis. Just concluding here, explainable AI can be used to render opaque models transparent. Explainable AI, however, is just more than a solution to a problem. It can also be used to achieve certain exploratory goals. I've looked at defining or specifying phenomena, identifying starting points, such as experimental starting points for causal inference, and generating possible explanations, such as algorithmic hypotheses in cognitive science. These goals are unlikely to be achieved through the use of ML models alone. Therefore, XAI techniques are exploratory tools in their own right. And I think that's a fairly interesting conclusion for philosophers working on scientific exploration, and hopefully also for scientists looking for different ways to explore whatever they are exploring. Just a brief reference here. I just yesterday got an acceptance letter from Minds and Machines that this work is going to come out in a paper on scientific exploration and explainable AI, co-authored with my former PhD student, Hannes Bolsen. So if you want, I can send you a manuscript. Happy to share. Cool. That's it.